All right, welcome everyone. In this video, what we're going to be looking at is internal forces in members. So as a review, we have talked about these ideas of as a two-force member. And we basically said a two-force member has to be in either tension or compression. So if I have a member that is being pulled on, something like that with some force, this is supposed to be in line, equal and opposite force. What internal forces are is what's going on inside this member. So if I were to look at some kind of section AB and I were to cut it along AB and break it into its two separate parts, what I would see is that I have some kind of force. My original forces are still there. So internally, because I can use my whole sum of the forces in the x direction equals 0 and sum of the forces in the y direction equals 0 and some of the moments about any point equals 0 for any member, whether it's cut or not. What I would find out is that I have to have some equal and opposite force that's balancing this thing out. So I'd have a force here, I would have some kind of minus force there. They have to be equal and opposite to balance themselves out as well. And these two things are called internal forces. And in this case, what we call this type of internal force is an axial force. And the reason it's called axial is it's along the length of the member, this axial direction. So those are all pretty easy and somewhat uninteresting for two-force members. What we really care about are multi-force members. So let's say, for instance, we had something that looked like this, some kind of cantilevered beam, and this cantilevered beam might have a couple of forces on there. We'll have one straight up and down, we'll call that P1, and another one at some kind of angle, P2. And just like before, what I want to do is I want to know what's going on at some kind of section right here at, we could call this point B or section BB or something along those lines, right? If I were to section this thing, I'm going to cut it right at B and look at the internal forces. And what I notice is I would have multiple forces to balance out those forces. I'd have one that's pointing in this same axial direction, the axial force that we just discussed, but I need something that balances out this vertical component of those two forces too. So I have some force that's pointing up, and we're going to call that V, and V is going to stand for shear. I'd also have to have some kind of moment, because I have some moment going on here. And I'm going to call this just B of X for my axial direction. So whenever you cut these things, these are the three internal forces you're going to be looking for. The first one I'm showing, is VB, and that is our shear force at point B. Now that shear force will always be the force that is parallel to your cut. And the other force that we already talked about was our axial force. Now that force needs to be perpendicular to our cut, meaning our cut is here, perpendicular to that would be in this other direction. And last but not least, we have this M at B, which would be, we can define as an internal moment at B. We can use our statics equations to find those things. So we can use some of the forces X, some of the forces Y, some of the forces Z. Of course, these are still on there, you know, something like this. As an alternative, what we could have done is we could have looked at the other half of this structure. So if we would have looked at that little nub that's coming out from the wall from B, I would have equal and opposite, based on Newton's third law, reaction. So I'd have some kind of V and a BX. My moment would be going the other way. You might be saying, well, what am I, you know, it doesn't look like I'm solving for anything. The way I would solve for that is I would start from the very beginning and find my reactions at the end. So there's probably, if we call this point A, there might be some kind of AY and an AX and a moment at A, right? So if I'm going to look at the left-hand side, I would start by solving for those three reactions using our statics of equilibrium. And once I have those, this would be my AX, this is my AY, no room in here, but moment at A. I can use the same concept with the other half. And now this BX and that BX have to counter each other. This moment and that moment would be equal and opposite, and this shear and that shear would be equal and opposite. So everything's balanced. That's a great thing about statics. Everything's equal to 0, so everything has to balance out. But if that was a little confusing, let's go ahead and take a look at an example, and hopefully that'll clear you up. All right, so for this example, what we're trying to do is find the internal forces at point C. And like I said, you can look at the left hand or the right hand side of point C. In this case, I do think it's a little easier to solve for the external reactions first. Meaning, if I were to draw all the reactions I have on this metal structure, ACED, I have a tension in this rope. I'm going to call that E of X. And then at point A is a pinned connection. So I have an AX and I have an AY. There is no moment at A because it is a pinned connection. From static equilibrium, or using my statics, some of the moments about A is equal to 0, I end up with this EX times 1, and once again, this is counterclockwise being positive. EX times 1 minus this 200 times 2, 3, 4, and then also minus that concentrated moment of 800 is equal to 0. So I end up with EX equal to 1600 newtons. And from some of the forces in the x direction equals 0, I find that AX must be equal to 1600 newtons pointing to the right. And from some of the forces in the y direction equals 0, I'm balancing out that 200, so I end up with AY is equal to 200 newtons pointing up. So once I have those three reactions, now I can break it apart. And let's start by looking at what would probably be the easier side, the left-hand side, because there isn't as much going on over there. And I'm putting in these external reactions, so I know that I'm pushing up on that end of 200 newtons. This is point A, and I'm pushing in with a magnitude of 1600 newtons. I'm drawing the same three internal forces that I'm always looking at. I have a shear in the C direction. Now I'm assuming it's direction. I'm looking at it and knowing what direction it's going to go because I know my sum of the forces in the Y. You could guess it's going to go down, and like I'm doing, and if your signs don't work out, you know you guessed wrong. The same context, I know that there's going to be an internal force, an axial force, that has to be pointed to the left because the 1600 is pointing to the right. And then I have a moment, internal moment at point C as well. So those are my three directions, and once again, you can guess what direction they are. We'll talk more about signs next time on what positive versus negative mean. But in this case, let's start with some of the forces in the x direction equals 0, and if I do that, I have 1600 going in the positive direction minus FC equals 0. So my internal axial force is 1600 newtons. And from some of the forces in the y direction equals 0, I have the 200 pushing up minus VC pushing down, so I have a shear force at point C that's equal to 200 newtons. And last but not least, I have some of the moments about the cut is what I think would probably be easiest here. So that's usually what I do. It helps me to visually think about what's going on. If I were to put a pin right there, I see the 200 pushing it this way, and that's what I have to counteract with that internal moment. So in this case, the way I have that moment drawn, I'm still saying this way is positive, right? So I have my moment at C minus this 200. Its lever arm from point C, if I go back up, was 1. So times 1 is equal to 0. And so my moment at C is 200 Newton meters. Now I haven't been putting directions on here, but that would be counterclockwise, and VC, since I assumed it was down, would be down, and FC would be, pointing to the left, something like that. As an alternative, I could have looked at the other side. If I looked at the other side, I never would have had to solve for the reactions in the first place, right? So maybe this would be the more efficient way. I don't know, maybe it's 1 in 6 of one, half dozen of the other, or something like that, but too big. Let's see. So if I drew a little nub here, so I'm putting all my external reactions. If I cut it at point C, I have this 800 over here, 200 pushing down. Oh, I would have to solve for my external reactions anyways, because I'd at least have to know what this EX is equal to. I have to know that's equal to 1600 newtons. After that, at point C, I have my my FC, my axial direction. I have my VC, and I have my moment at point C. Sum of the forces in the x direction equals 0, and just like before, what I would see is that FC is equal to 1600 newtons. However, now it's pointing to the right instead of the left, because we are on the other side of the member. So I don't know, you could note that these are always going to be equal but opposite direction. That allows that internally that these forces in essence cancel each other out. So what we want. From the sum of the forces in the y direction equals 0, what I see is my VC is equal to 200 newtons, just like before, but now it's pointing up. And from my sum of my moments about the cut is equal to 0. It's probably the hardest one, right? I have my moment at C, which I have drawn as positive, and then I have plus this 1600 times its lever arm of 1. I have minus this 200 times its lever arm of 3. And this 800 is also in that negative direction, is equal to 0. So I end up with a moment at C that is equal to negative 200 Newton meters. And the reason it is negative is if I look how I drew this thing, I drew this as counterclockwise. Well, over here, I'm also saying it's counterclockwise, so that's good. So what it really means is my moment at C is equal to 200 Newton meters, but it has to be clockwise. Because remember, they have to be equal and opposite. It just means I drew it wrong originally on my free body diagram up here. I'd like to say I did that to test you, but in all honesty, I just was going too quick. So I hope you found that somewhat helpful, and I look forward to talking to you soon. Thanks.